I'm privileged to invite Dr. Bijoy Krishna, IIT Madras, a prominent researcher in field of photonics, to the stage. Please join me in welcoming him as he shares his insights on the latest developments.
So, good morning, thank you all. Also, I'm grateful that the organizer, Dr. Amit and Dr. Gopal, actually invited me, giving the opportunity to talk a little bit about our research progress in the area of Silicon Photonics and quantum circuits and systems. Unfortunately, I could not attend morning session yesterday, but since afternoon we have our three prominent talks, Gopal Radhavan, and then Matan, and then Madam. So in three talks, I think if I summarize, take home, I am not expert in quantum information, quantum computations, but I am a technologist. So if I take some message from three of this talk is, first one is that, the question about quantum supremacy and where we are, Dr. Radhavan actually mentioned. So a lot of things have to be done, what is doing before things. So that is one thing, I also agree on that partly. And the second thing is that Umakant presented about ion-based quantum computing and his experimental setup, etc. And he also mentioned that it is relatively easier that ion-based, ion key, all this type of quantum processor relative to the superconducting qubit, Josephson Johnson's. But what we saw that it is not that trivial also, that is also very difficult to implement and a lot of control, a lot of things required. And today also Madam presented nicely how to visualize qubit, along with qubit, entanglement, correlation, all sorts of things. So visualization is very important before you go for something to implement. And as a technologist, I always feel how to realize. So theory, then visualization, then ultimately realization for practical applications. So realization is my motto, and alongside this, I just want to mention one thing after listening all these talks. So just a small historical background about something other technology related. So in 1947, transistor was invented, and then people started working on integrated circuits, and then that integrated circuits and a lot of investment gone into that, and that is how today we see classical computer, high performance computing, all those type of things. And then in 1960, around that time, laser invented. So solid state laser, semiconductor laser invented, and then people thought that we have the photons now. Instead of electron, we can generate photon. And then this photon, if you have some kind of photonic integrated circuit or so-called optical integrated circuits, that can be much more faster and that can actually eliminate all the electronic transistors, ICs, everything. So there are two parallel community. One is established, a lot of investment, semiconductor industry, silicon-based technology, CMOS foundries, all those type of things are there. And another community, but mostly physicists and physics-related applied physics technologists, those type of community started thinking, dreaming, integrated optical circuits, all optical, processing, everything. But they were struggling to find a unique material, like silicon, whatever done for electronic industry. So they tried many materials, and ultimately towards the around 1980 or so, because of their relentless research, long haul communication, high speed communication, internet, everything happened. But the dream of replacing electronics IC electronic integrated circuits actually started reducing. Okay, and around 90s or so, 1990s or so, it is almost dead, integrated optical circuit. It is ended up with certain kind of discrete component like, okay, 3-5 laser, modulator, and some kind of high-speed photodetector, and you can assemble them and you can get some kind of box for transmitters. That type of things happened. But around 2000, the integrated photonics revived again. How? Because this transistor electronic industry was traveling again to continue Moore's law, doubling the transistor every 18 months. That actually having to have some kind of problem. Then this photonics community came for a revival. So what is having their limitation, that is famously known as electrical interconnect bottleneck. So as you cram more and more transistors, billions of transistor size reducing, and their interconnect lines thickness size also reducing, their density increasing, so their apparent additional RC constant was increasing, so high speed communication is having a problem. So then it was tried to build silicon photonics technology such that those photonics devices can be fabricated using same fabrication process, same fabrication foundry, same infrastructure, such that wherever needed, electrical signal can be converted into optical signal, process it optically, high speed data, enjoy your bandwidth, 200 terahertz frequency, carrier frequency, and then you collect the data again, convert the electrical signal into optical signal into electrical, and then feed into your logic. So that is how photonics and electronics, they actually now it's a mainstream technology for semiconductor industry today. So my take is that today, whatever we are thinking that once quantum computer comes up, so classical computer will go. I don't think so. I think the take is that even quantum computer, whatever we are demonstrating everything, for driving quantum computer you need classical computer. So that is one thing. So in my opinion, where is the limitation, where is the bottleneck, similar like electronic industry, that particular part will be filled by quantum computation, quantum acceleration. People started talking around that thing. So I think we don't need to be very excited and very pessimist also, but we have to drive the technology, visualization, realization we need. A lot of application will come. So that is my take. So as a technologist, photonics technology, silicon photonics technology, we started around 2006, and technology started developing. Just thinking that we need to create some kind of ecosystem, value chain in the country. Just some idea, some paper, some real visualization is there. We just start realizing things. It's not, to me it makes no sense. Unless and until you have the value chain that it can be scaled up and ultimately it can be translated for real applications. Otherwise it will be just academic interest will be there, and we can enjoy, excite, all those type of things are there. That is fine. But for technology strength, technology development of the country, we need to look for value chain, ecosystem. So that is how we have been trying around silicon technology, semiconductor process complementing technology, CMOS complementing technology. So with this background, I just start a little bit of presentation here, whatever we have been trying during last several years, 3, 4, 5 years, maybe, around silicon photonics technology towards quantum computing, quantum communication, scalable, implementable, and viable, robust. So that those type of things over is the objective, and around that, whatever ecosystem is required, we have been trying. So first introduction, a little bit of silicon photonics I will be asked to. It has been started, it is already 20-30 years old technology. And then chip scale quantum photonics. What are the contemporary challenges? then major thing is that you need photon sources, real photon sources you need for quantum computation. And for that, not only the generation, you need kind of good quality photon sources so that you can use them for implementing different type of gate operation or superposition, entanglement, all those type of things, recipe required for quantum computations. I will be discussing that area, the third bullet point which you see, that is the area we have been working for the last 3-4 years. And then ultimately future challenges and our reports for silicon photonics enabled quantum circuit systems that we are taking up. So this quickly, this is in 2006. This is the guy Rulbers from Yale University. Started developing some of the photonic components in silicon platform using silicon electronic foundry fabrication process, and promoted some components like modulator, waveguide, and then gating coupler for laser coupling, light coupling, and photodetectors. So that is how a lot of academics started exploring, designing different type of photonic circuits using existing billion-dollar foundry across the world, and started progressing. Before that, of course, around 2000, Intel invested a lot of money to develop their own silicon photonics technology. This was actually open for the whole academic community. And in the same time, same year, 2006, we started in silicon photonics with very rudimentary level technology, and by 2021, yeah. So by 2021, we got substantial funding from our Ministry of Electronics and Information Technology to establish Silicon Photonics Center of Excellence, or Center for Programmable Photonic Integrated Circuits. Yeah. So it was inaugurated by Ministry, just a skip. So the thing is that our center, we are targeting starting from design, fabrication challenges, and system in package, so that we can deploy in the field for testing purpose. So these three areas we are looking for: quantum key distribution chip, transceiver, and then quantum information processor chip, computation related, and microwave photonic signal processor, physical sensor. Mostly, I think these areas, I think here all the audiences are there. Some of the chips we have designed, fabricated, and now tested. They are working fine. We are just packaging it for RF related packaging required for operation. That is our own indigenous design, fabrication, and testing is successfully tested. We will not be working much on this, telling much on this QKD related things. And this is where actually you see the industry landscape for silicon photonics, not only for certain application, optical interconnect application, data center application, etc. Most of the companies, they are actually big semiconductor giants. So they started silicon photonics technology, and they are also considering the silicon photonics technology for quantum photonic processor and TKD chip, transceiver related things, many other applications of course. And out of them, handful of them are like Xanadu, PsiQuantum, QuickS. These are the frontrunner to silicon photonics processor chip application, testing, all those things. So everywhere is there in India. Some startups are there, but I think not up to the mark. We have to go a long way. And you see, this is a little bit market size for silicon photonics. If you see that this white pillars, it is in 2022, and what is going to happen in 2030, and out of which if you see, the quantum computing market right now very little, but it is growing. Little means most of the funding going to superconducting, all other things. But many other applications there. My estimation is that by 2030 it will go up again because a lot of investment, a lot of industry coming forward. okay, how the silicon photonics, quantum photonics market for silicon is growing, how it will grow. We are somewhere here. This is the projection, and this is what the technology prediction for silicon photonics industry using CMOS foundry process lines. And this is the prediction for International Photonic System Roadmap 2030, where they are targeting that photonics and electronics, both systems, both components together can be integrated in bulk silicon, where this part is for photonics and then this part is for transistor electronics. And you can have also low loss waveguide like silicon nitride waveguides also you can integrate, such that you can, for routing purpose, low loss things you can do that. So this is the roadmap ultimately. Ultimately, if you do in bulk silicon, the cost everything will be reduced dramatically. Right now, what is happening, this part, the silicon on insulator wafers are available for photonics as well as digital electronics. And this part, some of the high-speed electronics are getting done on bulk silicon and germanium. So, with current technology, they are both photonic side and electronic side. They are fabricated using same process line, but different run. All the photonics chip is fabricated, a little bit relaxed technology node required, and very critical technology node required. Then you are using normal other run. And for driving your photonics and electronics chip, they are actually either flip chip bonding or board level connections, everything being done. So this is the roadmap, ultimate roadmap 2030, it will be coming forward. So if we are thinking to implement quantum photonic processor, chip, etc., we should keep in mind that industry going in this direction. So your ecosystem, everything, scalability, affordability, everything, if you just think about that, this should be kept in mind. Yeah. Now come back to our major problem right now, what we are facing, chip scale quantum photonics, contemporary challenges. So this is an ideal quantum photonic processor. Actually, people are dreaming to have in silicon platform using semiconductor fabrication process. What you need a photon source. And then this photon source, I think normally if you think of that those who are working in bulk, they are using the kind of process, SPDC, spontaneous parameter down conversions process. And in silicon, this SPDC is not possible, little bit weaker process, spontaneous Fourier mixing process people use to have kind of entangled photon pair generation, and then also you can have some kind of pure photon generation, everything you can do. For that, this is non-linear process, a little bit power required in the milliwatt range, but you will be generating maybe single photon level. So additional pump, you need to actually suppress more than 100 dB on chip. Then only photon, actually pump photons will not propagate and they will not actually create additional noise and also detection problem there. So you need a pump rejection at greater than 100 dB required. So 1 milliwatt, if you just attenuate to 100 dB, then you can come down to dark count rate level. And this thing, rest of the things, you need a just kind of interferometrics, beam splitter, phase shifter, superposition and entanglement, all those type of things you can do here. That is actually passive and a little bit of active control required. Where you need less than 0.1 dB per centimeter loss at least to get a good fidelity and good quantum photonic processor. Right away, people already achieved 0.1, and if you can integrate silicon nitride waveguide, some people started working on that, then you will be down to 0.01 dB per centimeter. So this part is very good. What people are doing, quantum photonic circuits today, this part most of the time off chip, and I will be talking this other part that is also off chip. And major, this part they are processing. So this you need a large scale unitary operations, all those type of things. That part actually is the food for today most of the time. And then you need a single photon detectors with a very high quantum efficiency And because this generation, on-chip generation rate, you can say that in the gigahertz range, megahertz range, you can think after considering losses, etc. You cannot afford that any detection goes away out of these things. So very high quantum efficiency required. So people are targeting like superconducting nanometer photo detector, SNSPD. So that is actually can be fabricated using semiconductor foundry easily. But problem is that you have to operate it in cryogenic temperature. So if you operate that in cryogenic temperature, you can think of that what will happen to the photonic circuit here. Fortunately, photon does not sense temperature because its velocity can change, but photon is an energy packet, right? So it will not be affected. So this part will not be a problem. Problem will happen probably in the phase shifter, how you are creating some heat. That heat may affect that thing, that has to be solved. That's a problem. But people are like Quantum, they are tied up with global foundries. They claim that they have designed SNSPD and chip, etc., which can operate at 4 Kelvin temperature. They can operate, and they are announcing big announcement. They are doing by 2030. They are saying that 1 billion qubit quantum processor will be launched. So that is one problem. I know that. I don't know how far they are, but their announcement says. And rest of the thing is that control electronics. Because entire circuit you have to drive by some kind of external electrons, on-chip fabrication, cost will be reduced. So that fabrication process is not a problem also. Right? It is good. And feedback electronics, you can do everything. But again, if you are thinking about cryogenic operation, that means this electronics also need to operate at 4 Kelvin temperature. When you see that IBM quantum computer, etc., they have some kind of temperature gradient where electronics sit in little bit higher temperature. So their electronic circuit designs are at 4 Kelvin temperature. So Quantum also thinking that that can be integrated together, so entire thing can be done. So far it is actually a lot of promise, but a lot of challenges there. And we have been working this part and some work because this you need a very good photon source and pump involvers. And this part, of course, we are very good at. We have demonstrated, some of the results will be there. So after this part, we can do in our own design. We have all the expertise, we have foundry collaboration, and this part, for the moment we are doing off-chip electronics for high-speed electronics. Some of the low-speed electronics also we are co-integrating together to drive all this interferometer part. So this is our efforts, all round efforts going on at IIT Madras. So this is our design, preliminary design of our photon source. It's not so simple to get it on chip scale. This is our chip, it is partly shown, where a ring resonator is there. In ring resonator, if your pump laser comes and it is resonating to one of the resonance wavelength of the ring, then the field strength will enhance in the ring. So once it is enhanced, the neighboring resonance positions, you can actually generate signal and idler. Okay, so signal and idler and unused pump will come out. And in that case, you need a very good quality pump suppression filter to see at least gigahertz rate signal and idler. Once you get that pump suppressed, pump should be suppressed such that it should not reflect back to the ring because it will destabilize again. So after that you need to demultiplex, demultiplexing can be done. That also you need very high extinction. We can go up to 60 dB or so extinction by using a unbalanced active Mach generator. And before that, one important part is that you need to integrate such rings, thousands, millions on chip. So you need that much power, laser power. Even though one ring needed 1 milliwatt, so you go for 1000, that means 1 watt power. 1 watt power required. So in that case, you need some kind of that many pump laser, or what you can do, you can use a pump laser, you amplify, you can split, so that all the pump can go same way If you are going for modular pleasure also you can use for pure photon generation, everything that is possible. So that thing also needed. When you amplify, that is possible. We have estimated some results I will be showing very quickly. The thing is that once you amplify, you get this type of spectra. You have a pump and associated amplified spontaneous emission. Okay, all these photons are there. And where you will be generating your signal and idler here. So that will be buried under the noise, all this amplified spontaneous emission. So first thing what you have to do, you have to clean up this pump. So you need a filter like this. The pump actually going up, all the AC generated, that should be suppressed. That should be suppressed to the dark control level. So that signal and idler will be revealed even though you filter it out. Yeah. So that is actually has to be very broadband also. And you have to design that, not available today in the market, you have to design on chip. And we got some success on that and we are some results. So this is the one part in the source side, and that is only one photon source. And then you can go for entanglement or superposition, all those kind of things. You need to integrate many of them. So it's a kind of, if you can think of billions of transistors could be integrated together in using semiconductor technology, why not? Here also possible. Here a little bit larger area required. Yeah. Yeah. So I think I will quickly go through that, how we have designed our ring resonator and pump and signal idler, phase matching conditions, and field enhancement inside the ring pump. And if you are using one of the resonances as a pump, signal idler will be generated and can extract them. So this is fundamental standard things. And problem is that, I'll come back to this one, whenever you just analyze that, then generation rate, that signal and idler generation rate, you can just, it's a kind of big lot of parameters, meaning that radius, quality factor, photon lifetime, frequency, resonance frequency, everything is there, and you can also another figure on merit you can find that generation rate divided by used pump power divided by delta lambda bandwidth, resonance bandwidth, that's actually brightness. And you can see one important thing of the ring resonator, silicon ring resonator, is that it is not that whatever resonance I have shown in the previous slide. If you little bit increase the pump, not only your Chi3 process, Chi3 associated processes are there, like kind of two photon absorption can take place. Because you are using 1550 nanometer, exactly 2 photons will process the band gap of silicon. So 2 photon absorption means 2 photon jointly give up energy and create electron hole pairs. Free carriers created. And free carriers means it will again actually create some kind of conductivity change, refractive index change, as well as thermal temperature change. And because of that, you see this type of nature of the transmission characteristics. If you go forward direction, the characteristics will be looking like that, not like a Lorentzian set. It will be suddenly jumping up. And in the backward direction, if you tune, it will come like this. It's a kind of bistability. We have studied in detail. And what you have to do, you have to operate somewhere here, where pump, if you are launching here, that pump will be depleted in the transmission, that means that field is enhanced. So that signal and idler can be generated. And along with that, coupling coefficient also play a role. Where is the coupling coefficient? So that enhancement, critical coupling and electric field enhancement can happen. All these things we have studied. And yeah, I think I can skip this. So ultimately we could control, we could make some kind of phase signal, we could control so that we can operate at B position, we can program B position, and we could actually generate signal idler. Not only that, we also demonstrated we could separate suppress pump, and we could separate, and coincident count, if you see that it is just depends on how much time you are just doing. In the forward direction, backward direction, your generation rate will be higher, so that way you can program. So these are the issues we could solve. Yeah, and then another thing is that, as I mentioned, that you need to clean up your pump, suppress the AC source. So you could come up with a very compact filter like this type of structure. It is just a 35.2 micron Width of course I made with 500 nanometer. And if you zoom this type of device, there is a cavity and here is a heater so that you can tune the cavity, and we could get a filter tunability also. You can see you can tune anywhere you want to filter your pump, apply heater power and pump level you could do. And you see that is how we could achieve amplified laser. You have the AC noise. Here it is shown up to minus 80 dBm. That is the limit of our spectrum analyzer. It will be actually dark count level. It will be much lower than that. And when we pass through simple waveguide, we get this thing. And when we pass through our filter, you see that is come down to 80 dB. But actually, it is lower than that. It is actually dark count level. We have seen our SNS video also. So clean pump we could get for our photon source. So I've been told that I have 5 minutes. So within 5 minutes I just wrap up. So then pump rejection filter also on chip, very compact. We could achieve up to 673 dB. We need 100 dB. We could cascade one more, but we are trying to make only a single stage. It can be giving 100 dB. Yeah. So some of the results. And you know that the interferometric structure as a whole, if you see the entire structure step by step we can build, we have to design each of these blocks. Each of these blocks we can design, test separately, but you have to keep in mind that they must be integrated together for scalability purpose, for cost, and using the foundry effectively. And some of the actual maze architecture we have designed. Actual design, not only design, it is tested, it will work very well. You can actually get all sorts of superposition and as well as ring cavity, and their switching and their superpositions. And also now we are going for a tape out of this type of architecture. It's a maze architecture. All these numbered things you are doing, that is actually Magnetic interferometer switch. And in between, we could actually integrate silicon nitride low loss waveguides. And those things actually you can just use for different type of delay line interferometer, superposition effect, and as well as lot of circuit related things. Even we can use some silicon related things. We are thinking also to have some kind of rings, multiple rings. We can say that we can actually supply the pump power so that all that they can be used for source. So those type of things we have been targeted. Yeah, and finally, the just near-term quantum advantage to take. We are actually, I think, recently also, we have been planning and we are going to take out this circuit on 15th of February, and Janadu just announced that they have done already 12 mode Gaussian-Boson sampling. Gaussian-Boson sampling. So we have the circuit design, including Janadu, whatever they are showing, source is outside. So we are actually integrating source together. And the source part is this one for 8 different sources, where we needed to pump into resonances, and twist state will be generated in the central part. And all the components we have actually designed and they have tested individually. Now entire circuit is going to be fabricated and they will be coming here. Here are the building block, mainly means splitter, where you have to control the weight and phases. Depending on that, certain application we are considering about gram discovery, etc. And then SNSPD array we can put outside and we can test it. Hopefully in the next 6 months we will be able to show this. And yeah, so some of the collaboration, entire ecosystem of foundry partners Silicon. So they are coming, all the design, whatever we go, we can fabricate for free from there. It is not free they are giving. They also get a complementary advantage from us, particularly testing, PDK development, all those type of things. This was one of the highlight in UK Peak magazine that our collaboration with Silicon is going good. And then we have kind of key site collaboration is also going on. We are developing for electronic photonic design automation together for their use in ADS system. We have some startup also. And microsystem, ISMO microsystem, a long-time partner. We are developing, they have a very good facility for electronic IC packaging. So photonics packaging, fiber attachment, all those kind of things we have developed at IIT Madras. So together we are developing so that photonics chip can be fabricated. Some of these things are there, and some of the second highlight publication, recent publications. This part I don't want to skip, or particularly for students and those who are thinking like that. So for the moment, if you want to go for a kind of quantum photonic integrated circuit, you need also electronic integrated circuit for driving, controlling it, etc. But this is the red alarm with current design of photonic integrated circuits. If you want to go for, whenever we are going for Gaussian boson something, the number of sources and modes that are important. So right now we are also going after 8, we will be going for 64 probably, but if you just think about 24 modes, that means 20 source and detection, the chip size will be 160 millimeter square with current design, current fabrication process. And 4-inch wafer, you can have 40 chips. And if it is same thing, you go for just for 6-inch wafer, 8-inch wafer, 12-inch wafer, then 163. So wafer size big means you can get cheaper cost and scalability is better. So we are thinking that at least 128 required to get a good practical solution for drug discovery. That is what theoretically people predicted. And I see Sivasis was your collaborator also, he is also involved with us, working with us. So we are thinking that we will be reaching in next 3-4 years up to 128, and so that we can go for 128, and we are targeting 18-inch wafer with our Silicon collaboration. So this is the thing. Now you imagine that whenever you are going for 1024 for large scale, people are talking about million qubits, etc. 1024, 12-inch wafer, entirety, you will get only one circuit. One chip, full wafer, 12-inch wafer. So the challenge is that your design, photonic circuit design has to be much more robust, compact, so that you can reduce. Right now, whatever psi-quantum, everything, they are full wafer scale thinking, 12-inch wafer with global combination. And they may get only one circuit. And that, if that does not work, it will not work. Okay, so that is the challenge. So a lot of challenges are there in photonics, device design, circuit design, and they are functionally novel idea how to make the compact circuit, etc. So these are the things we should keep in mind. So some of the budget, also overall budget required, that power, how many DVR, how many ring regulator, magnetic interpreter required, heaters required, bond pads, all those we have estimated, and major thing estimated pump laser power required in milliwatt. So about 1.2 watt required if we go for 128, which is possible, quite feasible. So we have estimated to reach up to this one. So that is how our design going on. Thank you very much. So I have this type of application in mind. I just have time to explain. We have worked out how to go for a drug discovery for using our Gaussian boson sampling process, which is squeezed state. Here in the input control, there are some thanks. These are all my army. They are actually working day night, very much excited because of them. I'm just trying to facilitate all this. There are 12 PhD students, postdocs, dedicated technology officer.
Is like scaling is obviously an issue, but till date whatever has been done, so like how, what are the, is it still in the development stage or has it been developed fully? Like if we talk about post-processing, characterization and all that stuff.
Okay. So we assume that, okay, so we can just adapt directly. Major thing is that that's a realization. The hardware, because otherwise, whatever hardware will be developed by outside world or whatever people, Psi-Quantum or general, whatever they are developing, they are things you have to just keep on following. Because they will be actually giving the rules of operations, entire market, everything driving. So that is one thing, it is developing stage, and they are not, we are, I mean to say, we are not very far from them in hardware related issue. And we expect that all other things are, that's the electronic processing development. That challenges are there. So many things to control it, a lot of challenges are there. But I think that is not impossible. That is possible. Once demand comes, that will be developed.
Also, you mentioned about that pump power is an issue when we like try to integrate it on chip.
Right.
Can you state some other challenges which you face on a daily basis for the system on chip fabrication?
Laser itself. On chip. That is okay. Even if you on chip laser integration also, anything if you see that signal to noise, I am showing that because of the end whatever noise is there. But signal to noise, hardly you will get 50 dB. So if you are getting 1 milliwatt at 50 dB down, there will be noise signal. Some noise will be there, photons will be there. Noise. That is also called spontaneous emission. So that has to be suppressed. Even if you integrate, people are integrating like with chip bonding, chip and semiconductors on the circuit, they are doing. But in my opinion, that has a lot of challenge also. Just integration, showing one thing, but you need a very stable laser, frequency stability, everything, temperature control, and we are developing in silicon and insulator, thermal management, all those type of things. A whole lot of interdisciplinary technology development required. So things are progressing, and because demand is there, I think solution will come. Yeah.
From Patna. I couldn't. I
No,
missed
I
it.
didn't say institute from Patna. I think we haven't found a house in the country, and that is required anyway. Many countries not having foundry also, but in spite of that.
Gigahertz.
Yeah, generation rate quite good, but problem losses will be there. Okay, so that is the thing. But one good part of photons is that in comparison to other qubits, you see, photon loss means lost completely. It is not sitting there to make you problem. So if a qubit is a physical qubit, Josephson Johnson or defective, that will keep on giving you noise all the time in the chip, right? Here, our photon source, photons are coming out now. As long as it is not reaching to your detector things, you can count them that are not generated. Okay, just gone, sir. Whatever reaching based on that, you can develop. It may take a little longer time to create your all the sampling, all those type of things, probability distribution. It may get a little longer time, but I think loss is loss. You have to reduce that thing. So every photon you generate with so many things, it is very expensive. So you cannot afford to lose them.
Then you will have to compare with the gate depth.
How many length you can survive. But anyway, if you see, we have estimated that even if you just go for, say, maybe 100 switch process, even if you just see that, okay, the probability, whatever loss everything goes, you will lose maybe half of the photons if you lose, even 10% reaches also, that is good enough. That is good enough compared to a whole lot of other things. But a lot of challenges still there, but all these challenges, photonics related things, in my opinion, challenges are there, has to be developed, but no bottleneck I see in future. You have to keep on working and maybe reaching there, no bottleneck I see actually. Maybe a little bit bulkier, but compared to whatever other technology platform you see, if you compare to them, this is much more robust once it is successful. For the moment it is lagging behind them, because investment is more there. So coincidence rate actually it depends on how long you are measuring, depending on that we adjust.
What is quoted there? How long?
That is, I think, it was.
Scale was some nanosecond.
So it is. So that actually we can see.
That is a good window.
Yeah.
I'm
That is-
talking about rate. 300.
Somewhere this is. Yeah. So here actually we are showing hard, but it is a nanosecond. Within that it's coincidence coming, but it is only half an hour we have measured here.
Yes.
Even going to the window, they are asking about the rate at which
So
the
they
reading
convert.
by particular states.
Yeah. So just one thing. Yeah, that's so it is actually gigahertz. Whatever just what is measured here? You are measuring and then you are coupling with fibers. The fiber losses to chip to fiber losses and to SNSPD, that actually we are having about 20 dB losses there.
But finally, this is what is
No, this is on chip. On chip we have to recalculate. That will be moved. This is what we have detected. Ultimately, on chip you want to get, right? So that is the thing. And also, whatever the things coupling, grating coupler, whatever we have used, that losses can be. That's a first level measurement. So our estimation is that that will be much more. It can be. That is actually it is generation rate. Actually, gigahertz. We have somewhere we have so coincidence calculation here. For that, we need to just combine with the SNSP rate actually. That is right. Yeah. So component level test structure we are putting along with these. For that, intention is also to go for GHZ, all those type of generation things, all those type of things we are at least particularly for measurement based things. Now those things I think we are just getting confidence. We are making small structure. People demonstrated, I think Quantum demonstrated few. They are much advanced stage, and but when they are publishing.
Bulk of this, so you can translate
One chip today, ultimately, you see all the bulk optics. To buy, frankly speaking, anything bulk optics you buy, all those type of thing, already demonstrated something you demonstrate in the lab, then you have to think, maybe new idea also you are implementing. But thing is that you have to see what next. Can you make a robust thing, scalable, mass manufacturing, all those type of things? That's not. But here, that is the chance, is there. So, whatever I'm saying that this Quantum, they say they have done measurement based all these things, lot of advancement, but papers also they come out, but not the details of the things are there in the paper. You can get directly and copy.
You mentioned squeeze states, sir.
Yeah, squeeze state.
Similarly, can you generate cat states inside these?
Cascading means?
Cat states.
That I think we have not explored that thing. All these things we have not explored. We have to see that. Right now we are in this just sampling. Your sampling, whatever it means, that sampling we first get, then we can go for next level.
Thank you, Dr. Bijoy Krishna Das, for your enlightening presentation on Silicon Photonics devices and circuits. Your insights into the latest advances and applications in this field are truly inspiring. Now, I would like to request Shri Amit Saxena, scientist E, C-DAC Pune, to kindly felicitate Dr. Bijoy Krishna Das.